Alright, everyone, this video is going to talk about factoring polynomials. We're going to start out with learning about a GCF, or greatest common factor. That's kind of what it sounds like. It's the biggest shared factor. Factor meaning something that multiplies to be the value you see. So we're looking at 12p and 18q and trying to find what's in common with them. We'll notice that the variables are different here, so we don't have a shared variable, but 12 and 18 do have shared factors. Okay, so I'm going to list this out for the first one, but I hope we can think through some of these. 1 times 12 are factors, 2 and 6, 3 and 4, and 18 doing the same thing. We could have 1 times 18, 2 times 9, or 3 times 6, and I go in order so I don't miss any. Okay, and the largest factor between these is the number 6. So we can say 6 times some quantity equals this original problem here. So 6 times 2 gets me to 12, but the p has to be on there. Same thing with over here. We need a negative 3 to get to 18. Q goes along for the ride. On this next one, you'll see that there is a variable in common, that x shows up in both. But between 7 and 21, 7 goes into 21, so it is a common factor. We're going to write that 7 out first, and since x is shared, we'll write it. Really, we want to make sure that we're picking the lowest variable power that goes into these because it has to be shared. We want to make sure that value goes into both. X squared would not go into both terms even though it's the greatest part. So here, 7x times x gets us back to 7x squared. We'd have to multiply by negative 3 to get to that second term. This is really just the reverse of the distributive property where you multiply through. Okay, here, 7 and 9 do not share any factors other than 1, and we don't want to use 1 because it doesn't change the value of this. So we're only looking at the variables in this case. The k can come out, leaving us with that 7 and 1k for that part, and only the 9 on that second part. Okay. On every single trinomial that we factor, GCF should also be the first step. We'd look through all of our terms and see if there's a common factor. Okay, all of these have an a value of 1 because they're all quadratic equations with that set up for them. So quadratic is where your highest exponent is the number 2, and usually it comes in this form where there's a squared term, a single x term, and a constant, as you'll see here. So what we're going to do to factor these is actually set them into 2 sets of binomials with 2 terms in each piece. Okay, and so here's how it works. When your a value is 1, so there's not anything in front of your squared term, we can start out by always just splitting up your squared term into the variable times itself. We know y times y gets us to y squared. Okay, but then we're going to find the factors of our constant, or our c term. Okay, so kind of like what we were doing on that first problem, we're thinking about all the numbers that multiply to be 15. That's 1 and 15, and 3 and 5. From here, since this was a positive 15, our signs have to be positive positive or negative negative, and we want to build in the middle term. So we want numbers that add to be 8. The only ones that would work here are 3 and 5. Because it was a positive 8, it's plus 3 and plus 5. And how this works is it's really backwards from the process of FOILing. Okay, so here's our expression, and we're saying it's equivalent to the original because first times first is y squared. Outside terms are plus 5y, we like the number first. Inside is plus 3y, and last is 3 times 5 is 15. And once you combine those like terms, it's equivalent to the original. Okay, so we're writing in factored form because the next thing we're going to do after factoring quadratics is solving them. And this is a really nice formatting to solve quadratic equations. Okay, so let's look at this next one. There's nothing in front, so there's not a common factor. And that means x and x go first. We're looking at the factors of negative 10. And I want you to start out with just thinking about 10. So 1 times 10 and 2 times 5 are the only options. This negative means 2 things. one of our signs has to be positive and negative if we're going to multiply to be a negative. But also, when we go look at our number in the middle, we want to get there by having a difference of these values instead of adding to those values. So 2 and 5 would have a difference of 3, and we just have to make sure the sign goes along for the ride. So we have to think to ourselves, would 2 minus 5 give us a negative 3? Or would 5 minus 2 give us a negative 3? Okay, so 2 minus the bigger number is how we're going to get to a negative. So we'll do a positive 2 and a negative 5, and that is factored form. Okay, you can always take a second to FOIL back in your head to see if it matches that original expression. This last one here uses t, so we're going to start with t times t, and we're looking at the factors of 16 that add to be 10. Now, if you can think about what these factors are ahead of time, there is no reason to list them all out. Okay, I'm doing this for practice here. 1 times 16, 2 times 8, and 4 times 4. We're adding to be 10 since this was a positive, and we'd need a positive 2 and a positive 8 to make a positive 10, and that's factored form. Okay, these next one have an a value that is not 1. There's a number in front. So your first step to these would be looking for a GCF. In the ones that I've given you here, there is not a common factor between the numbers. Okay, so these would all be considered what's called frowny face factoring. It's called that because your first step to these is taking a times c, and I make a physical frowny face on the problem. Okay, so 2 times 2 is 4, and I'm doing the same process as before in terms of finding something that's going to work with 5. Okay, so 4 and 1 is my first thing I'm thinking of that adds to be 5. Okay, in order for this to work, we've got to build all of this into place. So starting out just like the last one, this would be a positive 4 and a positive 1. Okay, but the problem is this doesn't actually work with the original. So you take n times n, you don't get to 2n squared. If you take 4 times 1, it doesn't give you to 2. And here's the fix. What we're doing when we're taking 2 times 2 is we're adding a factor of 2. The problem with n times n is it was missing a 2. So we're going to divide everything by 2, factors included, and take a look at it now. So here, those cancel and those cancel. N times n is n squared. N times a half plus n times 4 halves is 5 halves. And last times last would be 4 over 4, which is 1. So now it's working for us. Okay, but this is really ugly factored form, so we are going to take a minute to fix it. So it says we want to reduce first thing. Okay, so this first one, 4 over 2, we can reduce, n plus 2. Over here, this one we can't, so we're going to leave it n plus 1/2 for now. And your very last step is to eliminate any remaining fractions. Kind of like what we did here is we multiplied. We're going to multiply by this denominator just on the piece that has problems. Okay, so here to here would look like 2n plus 2 over 2 is 1. And now, by doing that, dividing off 2 and timesing 2, they cancel each other out, and we're left with the original. Okay, so check it out. N times 2n is 2n squared, okay, plus n plus 4n is plus 5n, and last times last is plus 2. We are back at the original problem. Okay, so you probably didn't learn this method in school, but I do think using this frowny face method actually eliminates some frustration, because sometimes it's very difficult to think ahead of time on what combinations of factors would get you to the original. Okay, so let's look at this one. Again, there's not a GCF, so you're just skipping to this 5 times 9 is 45. Okay, and we're trying to find factors that are 18. If it's not obvious, we go through the steps again. 1 and 45. Okay, 2 doesn't go in. 3 and 15, and there they are, so we can stop. Okay, 3 and 15 add to be 18, but we need it to be a negative 18. Okay, so this is a case where we would need a negative and a negative. We know negative 3 times negative 15 multiplies to be 45, and add together to be that negative. Okay, so signs have to be the same when positive. Starting out, just like the previous slide, x minus 3, just plopping them in there, Okay, but the problem is that doesn't multiply to 5x squared, so we got to divide by 5. Divide by the a factor and reduce. Okay, so this first piece doesn't reduce, leave it alone. But the second part does. That is x minus 3. Okay, a lot of times you're just going to have one piece reduce, but sometimes both sides do, so keep that in mind. And then we're going to fix this by multiplying by the denominator on just the piece that had the problem. Don't do it on the second piece. So 5x minus 3 and x minus 3, that's your factored form. Okay, last one here, 12 times 6, that's 72. If you don't know that, you throw it in your calculator. And we're looking at factors of 72 that add to be 17. Again, if you know it right off the bat, just write it down. Okay, but if you need to go through your 1 times 72, 2 times 36, and so on, do it. The larger this number becomes, the more factors there usually are. Okay, so the better we can get at those timetables and recognizing our patterns, the quicker this process will be. Okay, in this case, we know that 9 times 8 is 72, and that adds to our 17 for us. So x plus 9, doesn't matter what order we write these, x plus 8, and we're dividing them both by 12 to fix our problem. Okay, both of these end up reducing, so 3 goes into both of these. That would be 3 over 4. Second piece, 4 goes in both of those, so 2 over 3. Now, here's kind of the shortcut to this. So realistically, I don't know if you noticed or not, but this denominator just ends up moving to the front here on both of those. So I can just take this denominator and move it there, take this denominator and move it there, and end up with 4x plus 3 and 3x plus 2. And that's factored form of that original. Okay. We're going to talk about some special factoring patterns. These would be really ugly to do frowny face factoring on, at least some of them, okay, because we don't want to take 16 times 25 and list all the factors. Y'all, there are a lot, okay? So we're going to talk about what's called a perfect square trinomial, and like it sounds, it has perfect squares involved. Okay, 49 is a perfect square because 7 times itself gets you there. 14 is a perfect square, same way. So the first and the last term of all of these are perfect squares, and with that's the case, we can check the middle term. Here's what I mean by that. If we were to take the square roots of these, 7 and 4, this middle term should be exactly double of what those are multiplied to be. So when we multiply 7 times 4, double that is 28, and that's our 2ab. Here, square root is 4, square root is 5. That's exactly doubled to get 40. Okay, and same process is happening all the way. Okay, so that pattern has to happen, but once it does, the factoring pattern is always the same. A perfect square trinomial factors into a binomial squared. So here's how it would look. Okay, you're going to start with a parenthesis squared, and this a and the b are just the square roots of the numbers you see. So the square root of 49n squared is 7n, the square root of 16 is 4, and we just have to match the sign in the middle, and that's factored form. Let me just show you why it works here going forward direction. Squaring something means writing it twice, and you did that in the previous section. Okay, first times first, 49n squared, minus 28n, minus 28n, and this is where that doubling comes into play, because you're going to see that twice, and then plus 16, you're exactly what you were asked for. Okay, so if you recognize it, it's really fast to factor these. Square root of the first one with the variable, sign from the middle, square root of the last one, and we're done. So this one here would look like 2x plus 3 squared. While we're talking about squares, there's also another one with squares, but this is called the difference of squares. There's only 2 terms. Both of them are perfect squares. It's called a difference because there's a minus in between. Now, you'll notice that there's no single x term. There's no middle term at all on these. That's because in the factoring form for these ones, you've got your squared show up when you multiply these through, but the middle terms look like a negative AB and a positive AB. They cancel out. Okay, so this one, you'll do 2 sets of parentheses, and you'll still do your square roots, But in your parentheses, you're going to have one positive in the middle, one negative. So here's how it looks. Square root of 4x squared is 2x, so I'm putting that in each piece. The square root of 9 is 3, so 3 and 3. But because I need to multiply to be a negative, I need one positive, one negative. That's factored form. Okay, same thing here on this one. We want to take the square root of each, so that's 4x plus 7 and 4x minus 7. You do have to watch out. Sometimes they're going to throw a GCF with you in a perfect square, so that could look like a 9x squared minus 36. There's a GCF that you would want to take out first here. Then it's still a difference of squares, so this would be x plus 3, because x squared is a perfect square, and then x minus 3. And that's it. Alright, so here's kind of to break down everything, how you know what to do when they're all mixed together. If you've got two terms, after doing your GCF, it's got to be a difference of squares or prime. It's the only options. Okay, when it's three terms, you want to check out if your first term and last term are perfect squares. Okay, then if not, look, if A is 1, remember you're just starting out and you know your factors have to be the same, x and x, y and y, whatever your variables. Plop in whatever factors of C, add to BB. And then frowny face factor if that A isn't 1. Remember, you got to take A times C for those ones. Okay, please, if you struggle with factoring, ask questions early because it will not go away all semester long.